Well, good morning everyone and welcome back. You have started watching my lecture on linear regression model development technique. Um, so we are trying to develop model using linear regression analysis, and in that context I told you how to get the equations um, which we need to solve to get the parameters. Okay, so again, very short recapitulations. You have data, you have segregated data into two parts. For model development, some data you are using. For testing, how beautifully you have developed the model, you will use the other part of the data. And then you have designed a predictor. This is your design, and it will depend on the kind of data you have. Okay, if the relation is linear curve fit you do. And one very interesting thing, my student and many has a confusion, right? Linear regression does not mean that you'll have to have a linear straight line. No, if I have data, I will show you, say, exponential, and then I can fit an exponential curve. So my predictor could be W0 plus W1x plus W2x square. So I have three parameters, W0, W1, W2, and same analysis technique will be valid there, and this analysis technique will give rise to linear equations in the parameter. Always it will happen. Okay, we will talk about that. So for that reason I am calling it linear regression analysis, not because of my straight line. My students have lots of confusion. This confusion should not be there. Linear because parameters, the equations we are getting in parameters, they are linear equation. This equation you have got, another equation you have got, they are all linear, isn't it? Because once you have the data, this is constant. You'll have to calculate. You have to calculate this. So this is constant, this is constant, this is constant, these are variables and they are linear. It means nothing like this. Okay. So that's why it is linear regression analysis. Okay, this analysis is what we are doing. And also there are so many other issues. We'll talk slowly but steadily. We have, say, a feature x. It could be another feature if my data train is like this, exponential, or it could be another features, right? So for each one, I am getting some theoretical value. My predictor is like this, so square, and I am summing them up to get my actual predictor, and this is called superposition principle. So this is applied only when you have linear model. So linear is also from that angle. So right now you can understand that this is a linear regression analysis technique because it is giving me a linear equation in terms of my parameter, not because this straight line. Anyway, so you have now two equations. This one, linear equation, another one is this. Okay. So how to calculate or how to solve these two equations? I always prefer, so take a pen and pencil, and I always prefer to make proper substitution so that you will not make any mistake. Okay. So you can substitute A because they are constant. A equals to this one, A, then B equals to this one, this is your B, and then C is this is C, and this is your D. Okay, so A, B, C, and D, I have made the substitution so that my equations will not be ugly like this. They will be very simple. They will be simple. Okay, you see, M W0 plus A W1 equal to B, where A, B, M, they are all constant. Okay, and another is A W0 plus C W1 equal to D. So this and this in simplified form are getting the same. Okay, clear? As we have substituted. And then, oh, it is again class 9, right? Standard solving two very simple linear equation, right? And you can just divide it by m, and then free W1 and making it this, and then divide 5, equation 5 with A, so W0 become free, and you got this, and then subtract 7 from 6, and this is gone. So this is a method of, very simple method of elimination method, okay. So this you will give, you will get W1. Immediately you are getting W1. W1 in terms of sample and nothing else. Summation of the samples, square of the samples, all kind of things, they are called constant. That's why it's non-iterative method. Just you calculate, you have the sample and W1 is known. Just solving this equation. And then similarly, W0 will be also known. So W0, AD minus BC divided by A square minus CM, where A, B, C, D are these, which the moment you have the sample, 500, 600, 700, 1000, you can calculate. Okay, simple program. So W0, W1 are known to you, and so now we are putting the values of substitution, and you are ending up in getting the value of W0 and W1. So once you have got the W1, W0 and W1, then your predictor is designed. So now with this data y, x, you have fit a curve which is a function of x, parameters by w, and this parameter you have determined using regression analysis. This parameter you have designed. So far whatever we have talked is how to design this parameter. Once the parameters are designed, that's it. It's a predictor. You will use it. Use it for what? For samples beyond your design range. So, for example, if it is COVID example, so if you have made a regression analysis for 15 day of March data, you can predict what is going to happen, what happened in February, what is going to happen in April, provided the trend of the data is not changing. This is very, very important. If the trend of the data is not changing, now these are the known values through regression analysis you have done. And with these known values, now we will plug in, okay, X, for example, in month of April, 2nd April. So what my predictor, now I will believe predictor, because now you do not have ground truth for range beyond testing or designing range of the data. So you have collected real data, you have made a model, and you are using this model for predicting for a zone for which you do not have ground truth, and ground truth will be predicted now by this. And more beautifully, it predicts the ground truth exactly, then your model is good. And for that actually we test. How to test? You see, you have set aside some data out of 500, 70% of the data means you have used. So 350 you have used, 150 you have kept. You have kept means for that also, for each x, ground truth is known to you. So you see that for testing, you put x, and now these are the, you are relying on these values, and your predictor is predicting something, and for that particular x, you have also ground truth. So you can calculate the error again, and if the error is within some range, for example, acceptable range, 0.01 or whatever. So error is too small, then you have done a great job. So test aim of the testing is this. Okay, you will have to check whatever you have designed. You see, this is very simple. You are observing the data. When you cannot observe the data, multiple regression you are doing, then you will have to, from your experience, you will have to design this predictor. It could be like many predictor could be designed as we are depicting here. You see, this is quadratic curve. Okay, because the data trend is such, you have decided that I should fit a quadratic curve. But again, this is linear regression model. And all these equations are linear in parameter. That's why it is linear regression model. Okay, curve, yes, this is quadratic curve. Earlier it was linear curve. It could be many other curves are there. You see, cubic curve. If your predictor is designed like this, where you have W0, W1, W2, W3, three parameters attached with x0, x, x square, x3. So the x0 is always, fictitious feature is always 1. So this is free. So you see, this is nth degree of polynomial you can fit. If the data demands that, okay, my predictor should be designed like this, you will have to design that. And then you will have to figure out, say, n is the feature, right? If the feature numbers are great, okay, then each feature will give birth to one equation, because you are differentiating, each feature is attached with a parameter, and with respect to each parameter during design phase, you are differentiating the error function, and they are giving, and thereby you are getting one equation. So each parameter will give birth to one equation. So if you have n is large, 100, the 100 such linear equation you will get. But don't worry, we have methods for solving linear equation, 100 linear equation, 200 linear equations, nothing today. So you can solve them, and since they are linear equation, right? So it's very easy to solve linear in parameters, because these are samples, they are constant value. The moment you calculate, they are some constant. So, so this is different kinds of curve, exponential curve you can feed, parabolic curve you can feed, logistic curve you can feed, any curve you can feed which your data demands, and you can use linear regression analysis. And sometimes you see we do not even need to differentiate. Yes, differentiation is required, but thumbs rule we can apply. For example, in quadratic function. So you have this, the theoretical y theoretical equals to this, okay? So loosely I am writing y, ground truth. So y, so how to get this equation? This will come actually after differentiating with respect to W0. But straight away, if I want to write, there is a thumbs rule. If you know the thumbs rule, you can just write straight away. This is a simplification, but it is coming from there. Okay. So you have y equals to this. So multiply that equation with 1 and sum them up. That will give you one linear equation in W. You can check it by differentiating that, by creating an error function like this and differentiating that. You can check. Then you multiply this value, that is y, loosely we are taking y. You multiply this with x, and then again sum them up for all the samples, I equal to 1. And then that will generate another equation in W. Okay? And if you do not believe me, you will have to check, you will have to construct the error function, you will have to differentiate with respect to W1, and you will get exactly this equation. So another equation how you will get? Just multiply it by x square and sum them up, x square and sum them up, and it will give. So both the side you are multiplying ones with 1, sum them up, giving you one equation. Multiply x, sum them up, giving you another equation. Multiply x square, sum them up is giving you another equation. If it's cubic curve, multiply x cube, sum them up, will give you another equation. So in this way, you can simply straightway write the linear regression equation. This is, by the way, is called normal equations. So another name they have. All these equations are normal equations. And we have several methods: Gauss method, Gauss-Jordan method, Gauss-Seidel method. There are numerical methods of solving simultaneous linear equations using Cramer's rule. You already know. Okay, they are very simple. So that's it. So you are free to choose your predictor. You design your predictor, and accordingly you create that many, through linear regression analysis, you create that many equations, and from the sample, and solve the equation in terms of sample, and just like this, in terms of samples, you know, the parameter value will be determined like this. And once parameter values are determined, okay, you know the predictor, and once you know the predictor, you use it for prediction. Okay, and before that, of course, testing has to be done. So you have test sample, test it. So this is all about very simple non-iterative method of developing model using linear regression. So in the assignments, we'll give several problems where you can do it by hand. So I want you to actually know internal detail what is happening, although very simple, but very widely used. And industry like this because they are simple but very elegant, and they solve our they solve many industry problems. Okay, let it be prediction of vaguely weather, then stock market, then housing price, then whatnot. If you do not want very accurate, it is sufficiently accurate. Okay, if you do not want to spend a lot of other, there are so many other sophisticated models, but this is the model first one should try, because this is simple, this is elegant, this is solves purpose, this solves the purpose for which the model is developed. So now, before going for non-iterative method, I would like to tell you that how can we now generalize this error function. So you see, our objective was to calculate error and minimize the error. And in that function, we injected our unknown parameters, and we determined those parameters by linear regression analysis. Now, can we do a little bit trick? Means also, you know that we have done square. I told you that this is for making error always positive, but it has greater implication. By making square, I am ensuring my error function is quadratic in nature. And also, for mathematical convenience, I have done this. I have divided my error function by 1 and m, half m. M is the number of sample and half for mathematical convenience. Why? Because you see, we are differentiating, right? And in the process of differentiation, so x square, if you differentiate with respect to x, then you get 2x, and so this 2 and this 2 will cancel out, and my expression will be a little bit simpler when I will not apply normal equation, I will apply iteration. Normal equation, you have something legacy of making it to 0, and so these 2 cancels out automatically. But now when we will use it more widely, the same function, and we will use it for non-iterative method, we will study them. We need to a little bit modify that function. That's why, so that by differentiating 2 will cancel out, and by divide it by m, it will be a little bit more simpler in expression. And the modified function is known as mean squared error function. So that's the take home today. So you have data, you can fit any curve, linear, cubic, quadratic, through linear regression analysis technique. Okay, so don't confuse. It's not linear regression. Is not linear straight line fitting. It can fit many other curve. The technique is called linear regression technique. Why? Because all the equations subsequently you are generating for optimization of the error function, those are linear simultaneous equation in parameter. That's why it is linear regression model. And we have modified a little bit the error function for our convenience, for mathematical convenience, nothing else. So up to this is clear, right? Then let us try to focus in doing so. What is the nature of this function? I told it is quadratic in nature. What does it mean? And can you just, with a pen and paper, can you just convince yourself that yes, by doing this square, not only we have saved that all the errors should be positive, but we have generated a beautiful function which is quadratic in nature. And the function name is mean squared error function. Very, very important, very important, objective function. Okay? So without this objective function, as you know, you cannot tune your parameter, because inside the objective function, you have injected the unknown parameters which are known to you with the help of sample through linear regression analysis. Again and again I am telling this, okay? So objective function is required and optimizer is required. Here optimization technique was calculus. In other, we will see that gradient descent algorithm will act as an optimizer to tune the parameter. So let us see that what is the nature of this J. Let us take a very simple model again, that this is a linear curve, and even I have some data. So this is my X, this is Y, okay, and this is my data 1, 1, 2, 2, 3, 3. These are my real ground truth data. And say I have fitted this, and further simplification I am doing because I would like to see in 2D plot that how the J function behaves with one parameter. So one parameter I am keeping, other I am killing. W0 equal to 0 I am assuming, and thereby without bias, of course, my design is heavily constrained, because always whatever your data is, it will pass through the origin, which is not desirable. That's why we keep bias and determine what is the most appropriate bias through training. Okay. So this is my function. J function is a single valued function now with W1, and so this is my error. Say I have 3 samples, right? 1, 2, 3, for which ground truth values are known to me. So through hand calculation, I am making it, and I have fit this, that Hx parameters by W equal to X. So this is just like Y equal to X passing through the origin. And what is the error? So these are my ground truth, and I have fit a curve through all the 3 points. So error is 0. Error is 0. Now I decide, no, I will make, because this is my decision, right? So I will make a hypothesis with 0.5 time X. So this is my predicted, and these are again ground truth. It remains same. I have kept them as usual. And now you calculate the error for 1. Ground truth is 1 and predicted value is 0.5. So error is 0.5 minus 1 square. Okay, this is the error. Plus for one sample. Second sample, same thing. Second sample, predicted value is 0.5 into 2, that is 1, and ground truth is 2, so 1 minus 2 square, plus for sample 3, the predicted value is 1.5, minus ground truth is 3, so this is the error. So you sum all the error, square and sum, and you get a value 0.58. So keep this. So you go on and keeping. So you have W1, you have JW1, and you have different values of W1. W1 actually was 1, you got 0, W1 value 0.5, you got 0.58, and thus you can just take both of them 0, that is your predictor is here. So you got your error. So if this is 0, you got error 2.3. So you are with me, right? So with pen and paper, you can go ahead and plot anything 0.3, 0.4. So these are W1 value, and you can calculate functional value, which is JW1. And this is exactly I would like to show you. You plot W1 versus JW1. You will see this is a parabola, right? And this is quadratic in nature. And this is very beautiful nature, because you see JW. So even if I cannot see the function in 2D, I can see, okay, I can. So what is your optimum value of W? Definitely this one. And this is unique value. All other value will not be optimum value, of, will not minimize JW. So this is the beautiful nature of the quadratic function. And we made square show that our objective function will behave always like this. It should not behave like this. This is very bad. Why? Because when you cannot see, you are running gradient descent algorithm, it may, I'll write here. So the global, the optimum value could have been here, but your predictor will might take this W parameters which are wrong. So we do not like such non-convex type of function. This is called convex function also. So our objective function should be convex in nature always, so that I can crank out unique parameter by differentiating that function. So far so good for today. That's it, take home, which you have learned that how to generate model, how to you need an objective function, very good looking objective function, which will be convex in nature, and mean squared error function serves that purpose. It's very, very widely used, because it is intuitively also very close to anybody's heart, right? You have predicted value, you have ground truth, so this is the error. So errors, you do square and do something like mean square, and use it, because here you have all the unknown, and use it for optimization. It's a great optimization function. It's a convex in nature, so that you can run any gradient descent algorithm, or you can differentiate, and you will get unique parameter value, so that predictor will be not known uniquely. So in many cases we will use mean squared error function. So with this, if you have any question, come to the discussion forum and solve all the assignments which will be given in the class. Till then, stay tuned and have a nice day. Bye bye.